So now it's recorded. Kill this, and start full screen. Can you confirm in Zoom that you see the main window?
Yeah, full screen, thank you.
Yeah, good, excellent. Hi to all of you here. Happy Monday. Another week in paradise. Yes. How did it go with the lab? Good? Okay. So that was a warm-up lab. So it will be somewhat, I hope, somewhat more complex again. So I'm explicitly asking you not to use Gen AI for implementing labs because I want you to learn the concepts behind what I will present. What will be presented during this week. And I somehow refurbished this presentation compared to the previous year. So let's see how it goes. So there will be, as a pre-taste, a spoiler. So there will be lots of equations. So I obviously suppose that you will catch all of them on the fly. No, that's not the case. I rather want to go in a fast forward manner through math, because I realize that if I will just use handwriting, it will take ages. Offline at home, so you can go slide by slide and understand the details. And again, for practical reasons, you don't need to apply this math. So at the same time, this math is essential to understand why certain things work the way they work, and why do we choose to do certain computations in a way how you will do in first part of lab 3, for example. But I want to start this. And by the way, so that what I'm presenting is the focus of my research. So that's what I do in research, contributing to the with some math and new applications. And but I think it's a very important part of machine learning and overall AI, as in this theory, our community advocates that high-dimensional random distributed representations could be a bridge towards human-like AI, general AI at the end. And we will, please interrupt me and ask questions. I mean, I want more discussion. So what we will, the ambition for today is to answer a question, why it makes sense to compute with high-dimensional vectors, or to operate in high-dimensional vector space, how in the whole world it relates to AI, machine learning, and whether it is beneficial at all. I want with this, I want to show you this very, very busy slide, but again, the question is very simple. I want to come back to this question later on. So in many areas of AI and down-to-earth machine learning tasks, like discovering new drugs, understanding whether certain molecules can be combined with others to form new materials. To understand properties of materials, for example, if certain combination of molecules, atoms, produce soluble molecules, or discovering certain relations or patterns in social networks. So all these tasks require working with graphs. So graph and graphs, as you know, is probably the most generic data structure. So all others can be, all other data structures could be seen as versions of graphs down to scalar. That's the most primitive graph. Okay. So a question, maybe you can answer now. So you have two graphs. You want to measure a similarity, how similar they are. So similar two graphs are. How you go about it? I mean, spontaneously. I mean, think graphs. So you want to, so you have graph A with vertices, edges, graph B. So you want to compare these graphs and speed out a single number, say, okay, they are 0.37 similar to each other. Yeah.
Is it a directional or binary?
Doesn't matter.
Like a heat map?
Heat map, no. Um, maybe. Maybe. Okay, but think about it. I mean, so it's not an easy question. Actually, it is a rather complicated question. Computationally, so the solution is computationally complex. It is actually an NP hard problem. So the complexity grows exponentially with the size, obviously. But it is important. Why did I mention this? Because so far, in the first theory module, we talked about vectors. So feature vectors, very simple cases. So like objects. We sample certain phenomena in the real world through a set of sensors, and we describe this phenomena through a feature vector. Normally, the number of sensors are rather low. So I mean, maybe tens or hundreds, maybe. But and there are different types of features and so. But nevertheless, so we have a feature vector, and feature vector is a term in machine learning. So you view data as feature vectors, basically, right? And then, so we define, so during this warm-up period or module, so I introduced the problem of machine learning. So essentially, so you should have an intuition that any phenomena that you observe at the end is kind of is an n-dimensional space where all these coordinates somehow are located, and hopefully they form a pattern. And then again, most of the basic notion in machine learning is to compute what you can compute. You can compute distances, distances, yes. Euclidean from Manhattan to Euclidean to Minkowski distance, right? Or if you remember on first class, I also mentioned that you can compute dot product between them. Or a cosine if it's normalized dot product, a cosine similarity. The first question is what is the difference? Just as a recap. So why would you go for say computing a distance versus computing a similarity?
Similarity as more is the way or the way it's pointing. So it can
Exactly. So like in this example, so again a typical example when supporting this discussion. So you have ratings of movies given by different people, and one person so responded on first three features 1, 3, 5, and another one is 11, 13, 15. Right, and apparently. And yet another one could be 113, et cetera, et cetera. So if you compute a distance, so the values can be quite large between these three cases. So that's, I mean, with the highest values, they will be, of course, further away. However, if these three features correspond to, say, a genre, so a type of movie, like a comedy. So apparently all three people, they like comedies, but maybe not to the same extent. So dot product in this case would or cosine would capture this the directionality of vectors. So two different aspects. In some cases in machine learning, both directionality and displacement used in a hybrid manner. Again, so maybe drifting a little bit away. So if you take transformers, so the basic idea behind attention is to compute a dot product between whatever you got from the encoder. So you have your attention matrices, you compute the dot product, and then you use this weighted vector further on. However, if you think about these LLMs, so there is a notion of positional encoding. So it matters on which positions so certain tokens appear. Well, it is also done in vector manner, and I hope after this class you will have at least an idea that it may be the case. But so this is an example that sometimes the distance between, say, tokens together with more directional similarity together produce a powerful effect. Again, that's on really hand-waving level. Now I want to make this kind of leap, a big jump from using terms distances or dot product similarity to a general definition of a measure in a vector space. And a general term for a measure, as a general term, we will use word kernel. So when you hear kernel in this context, in the context of machine learning, it is a measure. But again, so this is a generalized definition. So if so you should understand it as a function that outputs a number that corresponds to certain similarity. So dot product is the simplest measure. So the dot product itself is a kernel. That's a definition. But then I also want to connect to the topic of last class. So when we talked about SVMs. So when we talked about, so very briefly, I mentioned at the end. So again, I should probably brought up the handwritings, but looking at you now, I will see whether you recall. So remember the final formulation of the optimization problem in SVMs. So you have this Lagrangian, and at the end you have this dot product. So I mean, after sophisticated derivation, you got an optimization function where you have pairwise dot product in the formula. And then basically what SVM does, so you remember, so it looks for border samples that actually allow to differentiate one category from another. And this is done by, well, as simple as the kind of comparing the pairwise dot product and somehow optimizing, choosing the points, the samples in the high-dimensional vector space that based on the measure, based on the dot product, pairwise dot product selects the appropriate model. Right, but then I said that the main assumption for SVM, for the classic SVM, or SVC, is that this samples that you analyze, or two classes, because it's a binary classification problem, they are linearly separable. So what does it mean? It means that in this high-dimensional space of your feature vectors, so you clearly can identify two clouds and draw, well, now I say a line, but essentially a hyperplane. So one dimensionality less than the dimensionality of your task. So you draw a hyperplane, and by characterizing the hyperplane really geometrically, you can decide whether the sample belongs to one category or another category. But then I also commented that many, or actually most of problems, real world problems, they are of non-linear character. So where the classes are not linearly separable. So which means that this measure, this dot product, is not very informative to decide about a separation. So here I found an animation that, I mean, so if you look at in this plane, so it's a class within a class. So and SVM cannot do much about it unless we do some transformation of this data. And what kind of transformation we want? Well, for starters, it can be. Sorry. I should stop moving around. So do you still see my screen in Zoom?
No, we can't see
No,
the
we
screen.
don't.
No, you don't. Oh my goodness. What about now?
Yes. Thank you.
Yes.
Okay. So yeah. Now, what kind of transformation? I don't know. That's a difficult question. So it's a very sophisticated. It's a complex problem to find such a transformation that actually makes one class more separable than another, or a transformation that builds a model that kind of repeats the shapes of classes. So one of the transformation is neural networks. So we will talk about backprop in two classes from now, in one class from now. So by tuning the weights of this distributed neural network, so you somehow approximate you approximate the boundaries of the classes. I also mentioned that another alternative method is to include high-level feature interaction, so to say. So like in this case, for example, if you have two features, A and B, so you can, for example, include, you can expand the dimensionality of your case and include, for example, sum of squares. And this is, again, this toy example that shows that it actually do this trick to kind of push all dots close to this center, to the bottom of a hyperboloid, and the others further away. And using this transformation, you can see that we transform the problem into a linearly separable one. However, to find such a transformation, as I said, it is difficult. But then what kind of researchers found, and that is what is called a kernel trick. You already worked with it in lab 1. So what you can do is, as I said, kernel is a function. So what you can do, you can try to non-linearly transform the distance or a dot product itself so that the resulting values are more informative from the point of view of separability. So you don't know what kind of underlying transformation is. Moreover, mathematically, you assume that you transform your task into infinite dimensional case. Infinite dimensional case, and on this infinite dimensional case, when you compute this kernel, this function k of x, y, for example, which is written in this form, which has a name radial base function. So then, I mean, this transformed measure is will allow you to separate the classes. Okay, the question is, can we still find transformations, explicit transformations of low dimensional vectors to high dimensional vectors, such that if you do a dot product between vectors, so it somehow would correspond to this equation over here. Why would we need to do that? Also, during the last lecture, I mentioned that the bottleneck of computational bottleneck of SVM is really maintaining and working with this huge matrix, gram matrix of dot products, pairwise dot products. And then on top of it, so you need to, well, here it's Euclidean distance, but I mean, it can be dot product. So you can, you should exponentiate it. So it's, and only then you can optimize the stuff. So a question is whether we can find explicit transformation to expand dimensionalities in a nonlinear form, such that when computing dot product would actually correspond to certain to these and other kernel functions. And apparently, yes, you can. So one of the methods, and again, so this is this method exists in the toolbox, in all toolboxes, and you should think of it as an instrument when working with machine learning tasks. It's called random Fourier features. So basically, so random Fourier features means that, so given vector of original dimensionality x, so some dimensionality, you transform it using number of trigonometric functions with randomly generated weights, so that at the end you obtain a high dimensional vector. I will show you now a numerical example how it works. But the idea is that when you do this transformation and compute a dot product, then it will correspond to, or it will be an approximation of this analytic form, which is called radial basis functions, which is true for infinite dimensions. Why, again, one would do that? Because if you find such transformations, then you can build very simple classifiers. You don't need, so you maybe, you can get away with linear regression. Because you know that by means of this transformation, you make data more linearly separable, so to say. But you don't know because for sure. So, but it is like as you probably discovered during the lab, choosing a kernel function is really a matter of trying. So you try several of them and see which one works. So it's like a little bit working in the blindly. Okay, so now the busy slides, but exemplifying what I just said. So here, what we have a two-dimensional vector, two coordinates, x and y, or x1, x2. And then we want to expand it to four dimensions. And to expand it to four dimensions, we use cosine and sine functions with two sets of weights, omega 1 and omega 2. So again, let us just trace this simple example. So we generate them randomly from normal distribution, so this omegas, and do the following. So what is, yeah, so we have x 1 and 0, and we have omega 1, 0.5, 0.3. So it's a vector multiplication. So 0.5 with 1, 0.3 with 0, plus bias. So we get 0.25. Then same thing we compute for sine with this omega 1. And similarly, we compute the other two components. So with yet another vector generated randomly, omega 2. So at the end, so we transformed our vector 1, 0 into four-dimensional vector with these values. And again, so I just traced an algorithm for what is called random Fourier features. The important point is that and that is behind this phi of x transformation. So x, your original, phi of x is random Fourier features. So now when you do that, so you can take this resulting vectors, make a dot product, and that will correspond, it's mathematically proven. So I can link, and I will link the original paper, that it corresponds to RBF, so above. Okay, so long story short, I'm converging. So basically, all these slides was to show that it makes sense to do nonlinear transformation in high-dimensional spaces, because mathematically it was shown that that in this case, with the proper transformation, so the measure of similarity, the kernel, becomes more informative or significant for separating classes. And again, so that path that comes from SVMs. So it shows that in theory, so it works with infinite dimensional representations. However, so later on it was discovered, so you can do explicit representations which has same properties, and the computations will be much more efficient. Okay. Maybe forget a little bit, or at least put on hold this idea with random Fourier features. So now we just think about the space itself, this random high-dimensional space. Why random? Because, for example, here, so randomness is the core of the algorithm. So we want to project into a space with certain a random process generating coordinates. So what's so special about these spaces? Now, again, irrespective to random Fourier features or algorithm that put us in there. So we have high-dimensional vector space, and we want to compute the statistics of similarities or the distances, as a wish. Let's put it similarities. We want to compute kernels, basically, between all vectors in this space. So yet another theoretical results from two mathematicians, Paul Levy and Vitaly Milman, saying that random, well, simply put, two vectors in the random vector space are nearly orthogonal with very high probability. That means that dot product concentrates near zero, or for example, if we talk about binary vector spaces, so Hamming distance concentrates around 0.5, normalized Hamming distance. That's also very important result to remember in the context of machine learning. So let me spell it out. Okay, very busy slide, but the math here is not very complicated. So we introduce a threshold for a dot product. So say 0.1. So and apply this result over here to find what is the probability that dot product between any two vectors in this high-dimensional space is greater or equal than this threshold. And again, so the higher is the threshold, the more similar vectors are. The lower, towards zero, they are orthogonal. So 0.1 essentially is very close to zero, as you may understand. So if you compute this bound, you will find that there is only one very small chance or a small probability that a dot product is higher than this small value on the one hand. But then now we reduce decrement t even closer to 0.5, and compute same thing, the same equation. So suddenly we have that 57% of chance that dot product is greater than this small value. So what it means that all dot products in high-dimensional space, they concentrated in a very, very thin area of values, so nearly orthogonal. So again, math is one thing, but on fingers, what does it mean? And you can try it yourself. So you generate randomly. So you see random number generator and generate. So you choose, for example, vectors of real numbers, and you generate them at random and check dot product. So in all cases, like 99.9%, so it will be around zero. Maybe that's even intuitive, but apparently it is not. And then, of course, so the higher is the dimensionality, the thinner is this corridor. So here again, so that's case when we look at a vector space, random vector space of binary numbers. So all coordinates are zeros and ones. And they can be any. So you can choose the number system as you wish. So in this case, it's binary. So and here you see normalized Hamming distance between any two vectors for different dimensionalities. So this blue line, the blue bars, is for dimensionality 5. Then somewhere, so here is it green one or what? It's 20, and so on and so forth. So here we have 10,000. So the higher dimensionality is, the more likely that you will generate almost orthogonal codes or vectors. And that's very good. We will, you will see how we will use it. It means that whenever you need a random kind of a vector with a low dot product, you can simply randomly generate it on certain dimensionalities without being cared about possible collisions. So, yes. But again, what we talked so far, we just talked about abstract vector spaces. First, I started with the fact that it makes sense to kind of expand dimensionality, so to place your feature vector into this high dimensional randomized space. And on the way, so this function, how you transform, also transforms the layout of similarity so that in that high dimensional space you compute dot product, and using only this dot product you can build classifiers close to linear classifiers. And then I also said that abstracting away from this transformation, the property itself, so one of the remarkable properties is that with extremely high probabilities, all vectors in this space are mutually orthogonal, which is interesting. But at the same time, the key word in what I'm talking about is still a vector. So we still talk about vectors, of course. That have certain origin and have coordinates of the end. And as such, all vector algebra is applicable. So you can take vectors, you can add them together, you can do a product of vectors. For example, you can do element-wise multiplication, Hadamard product. You can do cyclic shift of coordinates. You can do permutation of coordinates. So you define a permutation matrix that first position goes to fifth, fifth to third, and so on. So all this purely algebraic stuff you can do with these vectors. The interesting thing is that to see, so if you start with originally orthogonal vectors and you do these operations, and then you compare the similarities of the results. So how does it behave? So if you add two vectors, so you generated two vectors randomly. So the dot product is nearly zero. You add them together, and now you compare and you compute similarity of each of the operands to this resulting vector. And I mean, again, maybe it is intuitive, but it's an interesting trend. So the similarity of the resulting vector will be substantially higher than zero. I mean, compared to the with respect to the operands, because of course, I mean, it's a sum. I mean, both versions of vectors exist in this sum. Again, on fingers. If you take multiplication, so let's again already now introduce this word binding. Hadamard product, so multiplication of coordinates. So you generate, you have two random vectors, you multiply them, and the result is also a random vector compared to the operands if you compute the dot product. And same thing goes for permutation or a cyclic shift, which is a special case of a permutation. So a trivial permutation is a cyclic shift. So you take a random vector, you shuffle the numbers in a predictable manner. Again, the result of this operation the dot product between the result of this operation and the original vector is also close to 0. So somehow we can do these operations, but now we also have understanding how different operations modify the similarities of the original representations. So, okay, so that was a long kind of logical chain, I guess. We will be talking about a computational framework where we will represent everything: signals, scalars, even symbols, discrete symbols, as high-dimensional vectors. And we will introduce, we will make algebraic operations on them, knowing how they affect the similarity. And yet what we will do, so whenever we just need, let's say, a vector tag, just to assign, for example, to make an assignment, a unique assignment, we just randomly generate it. So thanks to the concentration of measure theorems, we can do it. But remember that we will work with very high dimensional spaces. Well, hundreds, thousands, or even 10,000s. But that's okay, thinking about biological brains which operates with the activations of millions of neurons for simple concepts. So now, all this lengthy motivation of vectors, I want to, with all this motivation, I want to come back to my previous question. So now, how to measure similarity of graphs? So that's a totally kind of different question or unrelated topic. Before break, I will let you go to a break soon. I just want to show you one of standard ways of computing similarities on graphs. It is called graph edit distance. So in essence, so you have two graphs, and you try to make one to edit, to remove vertices or edges in such a way to be alike with the first one. And depending on how many operations you do, I mean, this transformation, so that will contribute to the computation of measures. Again, that's pretty much everything I want to tell about graph edit distance. If you are interested, you can read about it elsewhere. But at the end, so this algorithm spits out a similarity measure that kind of counts all this number of operations and tells how two graphs are similar. Yeah, a simple example. So here we have vertices. Well, it's very trivial graphs, of course. You have vertices labeled AB and vertices labeled and another graph labeled AC. So it's a single edge. The difference is in the second label. So you want to compare these two graphs, and that's how it does. So you assume certain cost for different operations, like for deleting, inserting edge. The cost will be 1, and for substituting label, the cost will be 0.5. And then at the end, you say, oh, okay, these two graphs, they're 0.67 similar. But as you can imagine, so to do this, you really need to walk through all the graphs and do all these complex operations and comparisons. So in reality, so exact graph edit distance is an NP hard problem. requiring also large manipulation with large matrices. So a question to you, and again, maybe that would be a logical end of this lengthy discussion. Can we come up with transformations of graphs into a vector space again, so that you take two vectors representing two graphs, compute dot product, and somehow it relates to the similarity of the inner structure between the graphs? So that is the question, and how our high-dimensional space and algebra can help us with it. So let's take Ben leg stretcher, several minutes. So the question is to straighten the connection between graphs and vector spaces, and I said that so to me the analogy is rather of the same type as with that I meant with the kernel trick. So in that case, it was a vector space, and we just transformed to another vector space. But the idea is similar. So when transforming from some original representation, well, whether it's vector space or not, or something else, but the destination is vector space, and in this vector space we compute dot product, and this dot product corresponds to similarity in the original space. So whether it relates to an it's rather reduction to kernel trick, I would say. But now again, so I stated more of as a question. So can we find such a transformation? Because graphs is a symbolic construct, so it's a structure, and apparently. Yes, of course. Before I show you the next slide, you can obviously mention graph neural networks. Yes, this is a transformation. So it's a graph neural networks take somehow, well, they are able to walk through a graph and interface it to a neural network, and so at the end the neural network learns the vector representation of a graph. So that's true. But can we build similar encoder or transform just using the properties of vector space? So apparently, that's why I mentioned briefly about these different operations that you can do on vectors on high dimensionalities and their effect on similarity measures. So maybe now I just put it as a fact to either believe or to further verify. But using high-dimensional vector algebra, you can construct manually vector representations of all main major data structures. For example, something that is not shown here, a representation of a set. So you have number of items, ABC. You just sum it up, and collectively one vector will be similar to all of the components. So if you want to account for the order of items in a sequence. Then you need to make a position dependent encoding of this symbol. And now I will make a link in a few slides to random indexing. So that's what is happening there. So you essentially represent a sequence of symbols, which are random vectors, by modifying the some initial vector such that well, on the one hand, you know the transformation, so the position-based transformation, and on the other hand, so each new vector is orthogonal to the previous one. You can do representations of trees. You can graphs again. So at this moment, maybe it's I don't even want to spell it out. So what you will work practically with essentially is only encoding sequences. So you somehow were introduced to it, well, probably in a kind of just face it level while working with random indexing. But in the next lab, you will be manually, or you will be using it actively to for representation of n-gram statistics, what I will show. So the properties of hyperdimensional spaces, the idea of transformations to these vector spaces with the goal to get an informative or as informative for classification similarity measure altogether that are properties of computational framework which is called hyperdimensional computing, or synonymously it is also called vector symbolic architectures. And it has long history of development, essentially. So maybe one of kind of most relevant results was from Geoffrey Hinton. So he coined this term that to have that neural representations are vectors in high-dimensional spaces, and moreover, they are a special type of representation. So so that you should interpret like the whole pattern of representation at once and not position wise, so which is called distributed representation. And other people who contributed really to the algebra and applications of hyperdimensional computing. So now random indexing. So remember, we want to classify what documents or what did you work with in the lab? So was it synonym test, right?
TOEFL.
Huh?
TOEFL.
Yeah. So there's a synonyms test. So you want to build representations of words versus learn representations of words, embeddings. In both cases, we do talk about embedding of the original a representation in the original space into some high-dimensional vector space. And so in the lab, you worked with part of this random indexing that use this position-based encoding. So with an idea that the word of interest, the target word, is defined by its context. But now, again, so how to build such a system? If you start with all random representations originally. So, I mean, random representation, as I said, is easy. So you want so this is a symbolic case, and basically you say that all original symbols, or in this case the granularity is words, they are not dependent from each other, and as such you can just randomly generate the initial codes. But then you want to modify this original representation in such a way to to encode the context that so the symbols that come before the target and the symbols that come after the target, after the focus word. And again, so if all of this, oh yeah, sorry. If all of these words are encoded as random numbers, what choice you have here? So one maybe naive way of thinking, okay, so we put all the context together, so we just sum it up. But then we know that the resulting representation will be similar to all the vectors that are included in the sum. What does it mean, or what is the problem here? It means that you can you will obtain exactly same vector or a similar vector even for cases when the order of words will be swapped. And in NLP tasks, so the order of words is obviously matters. So that's why we say we can do much smarter. So we want to encode a sequence, so a trace of words. And how we do that? So again, starting from some random representation, you can take the original representation and permute it, well, in certain manner. So either to the left or to the right, some positions, and that will make the whole algorithm consistent. So you have a consistent procedure to derive position-based encodings of words, and when adding together, so it will actually implement a sequence, so encode a sequence. So similar schemes can be derived for encoding other data structures. Again, so I'm using this word encoding. So, but we are in the context of machine learning, and not only machine learning but AI. So everything's supposed to be. I mean, what is the place of these operations in the context of AI? One of the fundamental challenges in AI, which is not fully resolved now, is something which is called compositionality. So, we as humans, we are very good at constructing compositional representations on the fly. So mentally, you can easily combine a chair and a bird. I mean, two concepts together, whatever it will result, and you can operate with this composition in depending on the context. I don't know how. Neural networks, nowadays, I think I already mentioned it in a different context. Nowadays, it's very hard to make certain claims that neural networks cannot do that. Like Gen AI can do that. So if you, for example, prompt, so what is the composition of certain items? So it will give you an answer. The problem is how it is done internally, that is unclear. So, and whether it can do compositions on the fly or like in a straightforward manner, that's still unclear. So so in the context of machine learning, so this procedure, what I'm talking about now, you can see it as really a tool for representing input data. In the context of, in the greater context of AI, a possibility of manipulating vector representations using algebraic operations give you a path towards this on-the-fly compositionality. So something you will work with in the next lab. Again, so n-gram statistics. N-gram statistics for so representing text for classification purposes. So if what is it all about? So the original algorithm. So you in the original algorithm, so you would list all possible sequences, patterns of 2 or 3 letter combinations or character combinations, and and then you take this long and then you scan a text. And then every time you see a specific combination, you put 1 or you increment a counter. So, and in this way, so after parsing the text, you got a statistics of different n-grams, so combinations of letters. So what do you have? You have a high dimensional representation, but it's very high. It's, I mean, so if you have, so here is an example. So if you have 27 letters of alphabet, so you see the dimensionality of vector grows dramatically. So right. So what I will what I ask you to do in the second lab is to apply this vector symbolic algebra to come up with simpler vector representations. So what you will do essentially, you will construct a single vector which will contain a sum of encountered n-gram representations. So somewhat similar to a random indexing with respect to encoding, but not directly. So you will start with some random initialization of symbols of alphabet, and then you will encode n-grams in a similar manner. So A on the first position will be shifted once, A on the second position will be, so initial vector shifted twice, etc. And then, so you parse your document, you encode 1 n-gram, then second n-gram, and then you sum them up together. So basically, using this encoding, you will have a single vector which will contain instances of all possible n-grams accumulated. You get a lot of compression. So, and that is due to 2 facts. So, first, that you can, well, you have a tool to encode sequences, a data structure, in such a way that well, it is position dependent. So ABC is not equal to CBA. And secondly, again, you work on high dimensional representation so that adding original representations together would so the resulting vector is a kind of is an image of all the operands with respect to similarity measure. So the aggregate vectors for different language, they will have different similarity patterns with respect to the inputs. So that's what you will try yourself in lab 2. So what else can you do? Again, so still while working with sequences, for example, in machine learning, there is this kind of always a hassle of working with variable length sequences. So normally I mean you should choose how to do padding. What to pad with. So the zeros, ones, max. So depending on what you pad with is really can affect the resulting the result of classification. So here again, so if you do encoding of sequences in this manner, you always remain in the vector space of the fixed dimensionality. And similar sequence. And as again, so the important keyword here is that this encoding implements a kernel. So the dot product becomes informative for classification purposes. So, for example, here we applied this technique to analyzing patterns in Melbourne. So patterns of cars passing through different crossings. They had this Bluetooth readers deployed on traffic lights, and they basically recorded the passage of particular MAC addresses, and then had this huge database. So and obviously, so different cars, they pass through different number of crossings. So deploying these embeddings simplified significantly computations. Something different, something which relevant in the robotics domain, and the task of visual place recognition. So in visual place recognition, so a robot navigates through an environment, stores descriptors of frames from a video camera, and then the task is to identify a place when he puts in a random position. And basically, there are different ways in machine learning to come up with the descriptor of images. And again, saying a descriptor, so you can generalize it to any embedding. So there are different ways to produce embedding. So for text, for images, and this some embeddings, as you learned during the last module, they're learnable. So you learn them through by neural network supplying lots of data and such. Some descriptors, they are more of a feature engineering character. So you kind of you may, for example, scan your image and record pixels of certain intensity in a specific neighborhood. So there are feature engineering methods, in other words. But all in all, so this and different embedding mechanisms produce different kinds of embeddings. And these different kinds of embeddings, so they reflect different aspects of the underlying phenomena. So essentially, again, my message is that embedders, word embedders, so they do implement this explicit transformation. But in the board embedding case, so there is no correspondence to specific kernel function. So it just empirically it was demonstrated that comparing vectors has makes sense. I mean, from the similarity perspective, from semantic similarity perspective. So again, all in all, you have n methods for obtaining embeddings. all embedding methods result in vectors with different similarity layout between the results. And in different tasks, so this similarity layouts highlight different aspects. So, and of course, like for example, in the robotics case, so if you have this n methods or 5 methods, and each method spits out 4,000 dimensional descriptor. So then in total, you need to have times 4 memory per image. So what you can do, these are examples of algorithms you can check offline. What you can do essentially, again, knowing that you operate in this high-dimensional vector space, first you can align the dimensionalities, so preserving the original similarity, and this you can do with the technique which is called random projection. So you generate random matrix, Gaussian matrix, and then multiplying, which maps from the original dimensionality to target dimensionality. So you can align the dimensionality of the descriptors. And again, so it's, now since you moved into the high dimensional space, you can apply algebra. So you can say, okay, so now you have n descriptors, but we want to collectively process them. And due to the properties of sum or superposition, you can just sum them all together, and that is actually a typical move in or a technique in artificial neural networks. So even in transformers, so you get different representations, and at some point you add them together for certain purposes. So, and basically, so combining these descriptors into a single vector again, so you get kind of advantages of all of them at the same time. So what is that? Yeah. Maybe I can skip it. Maybe I come back if time permits. Another interesting application of this technique comes from a different domain. So, oh, sorry. This one first. It's a now we consider a multitask learning case. So you have a single neural network and several tasks to learn. So you learn, for example, you train a neural network on numbers, and then you switch to cats, and then you switch to dogs, classification of dogs. So in neural networks, this is an example of something which is called catastrophic forgetting. So when you train a neural network on a single task, and then you retrain it on another task, so the previous information is forgotten very quickly. So the quality of the classification decreases. Again, what you can do here, you can treat neural weights again as vectors in this high-dimensional space. And again, so that's a very reasonable assumption. So all weights are initialized randomly. So we are in this high-dimensional space, and then during the training, we just, as I mentioned, so we just transform the similarity layout. So what you can do, So before training another task, you can generate a tag of the same dimensionality as the weight matrix of random permutations. So you basically take your weight matrix and you permute the weights before training a new task. And then for the next task, you permute the weights again. And that permutation matrix, you call it context matrix, so which basically separates one task from another. And apparently that helps a lot. So what you do with the permutation, so you make the layout of weights orthogonal to the previous one. And the network, during training, so it doesn't destroy the weights that were trained for the task before. Again, if you're somehow caught by this superposition of many models and so on, so here is an article. I mean, another interesting stuff is again maybe in the same along the same line. So how to train a network for different physically same network on different streams of data, so that the network doesn't mix them up, essentially. So in this case, what you can do, so you have your original image. So normally you can do some random projection of it. That's a normal case. So you can assign a tag for each channel. And then what you actually input to the network is a superposition of two channels. So as you see here, so that is similar to this position-based encoding. So the only thing is that now your original vector is is an image. So what you get, you get two separate channels being superimposed into a single one, and the neural network trained on this aggregated representation simultaneously. Just checking your reaction. Maybe you have some immediate concerns. So what you do here? So you have an input. So you have you have images belonging to different classes, and you want to different cases actually, and you want to train on both of them simultaneously. So what you do, so this operation is this multiplication. So the key is a vector of the same dimensionality as the input, and by multiplication you kind of make it you move this vector into unique part of the representation space compared to this channel, and then joining them, so superimposing, so aggregates this channel back into vector of the fixed dimensionality. And then so it allows to train a physically same network on these two different data streams. Well, that's more for kind of use case demonstration. So if you need more information, so here is the name of the article. So final words. The final words are like this. So we started from the problem of transformation into high-dimensional space, so that the layout of dot products is such that makes observed phenomena more distinct or approximate or moves it closer to linear separability. And then on this high dimensionality, so the vector space themselves may have important properties. Like you can generate lots of symbols or orthogonal vectors, and that gives you a possibility to assign these vectors to symbols or tags, if you wish. And then again, since it's a vector space, you can deploy algebraic operations on top of them. And again, so these operations will result in different similarity layouts. Okay. Last word is that so these vectors, so I mentioned briefly, so they can be, of course, real valued. So in this case, you talk about real valued vector spaces. They can be binary. I also gave this example, but they can be complex numbers as well. So each position is a complex number. What is it good for? Well, it's good for several reasons. One of the main reasons is that so these vector operations become very compatible with modern or novel computing hardware, like, for example, spiking neural networks. Yes. So basically, if you want to know more, if you want to try some operations, so there is even a library. But again, for your purposes, you can implement all these basic vector operations yourself from scratch. So here are useful resources. I think this one is, well, I will correct it in the PDF. This one is a collection of videos. So on different, so I have collected them over the past 5 years on different aspects of high dimensional computing. And so here you will see all other related information. So hd-computing.com with all the recent publications. Yes, that's it for me. So I guess you will get it more when doing lab 2. But if you have any questions, so Discord, and you know where I fit. So okay, that's it for today. And see you later in Zoom.